Hello, everybody. Welcome along to a Data Science Festival sandbox session with our good friends from dunnhumby. You can always tell when it's a Data Science Festival week, actually, because there is always a webinar with dunnhumby that week. And I must admit, it's something I always really look forward to. And we've been partnering with dunnhumby for, I've lost track, if I'm honest, a good number of years. And they've been amazing supporters of the data community throughout that whole period of time. I think actually even going back to our very first year, I think it's 2016, 2017, dunnhumby were there running events in their office and supporting us at our conference. The thing I absolutely love with dunnhumby is that they're very community minded, but they're also absolute experts in what they do. And they're very forthcoming when it comes to sharing content, sharing insights with the data community. And many of our most popular videos on our YouTube channel originate from dunnhumby. And I'm sure today is going to be no different. We're very lucky to be covering a session on smart retailing, optimization techniques for strategic success. And we're joined by Aditi and Surbhi. Aditi is an applied data science director at dunnhumby, and Surbhi, senior applied data scientist. And we were joking beforehand, actually, about how long people often work at dunnhumby. And I think Aditi was 14 years and Surbhi's 10. So it's obviously a good sign when you're happy being at a company for that long. Or maybe, if it's okay, invite Aditi and Surbhi to turn on their cameras and microphones and come and join me. Come and join me on stage. So I'll come to you first, Aditi. How are you doing today?
Very well. Thank you.
Amazing stuff. And yourself, Surbhi?
Yeah, same here.
Good stuff. We were talking beforehand. We've got a jet set audience actually today. So Aditi's normally based in India, but is in the UK today. Surbhi, normally based in America, but is in India today. So we're covering a couple of time zones, and I guess there may be some of you joining us from around the world as well. So feel free to say hello in the chat. Let us know where you're joining us from, and yeah, it'd be great to say hello to some of you as well. We are starting to get into today's session. So what I'll do, Surbhi, I'll stop sharing my screen, and if it's okay with you, I'll maybe get you to share yours. Just as you're doing that, I've obviously called out that the chat is open, so it's always nice to say hello to people. We've got Oscar there, greetings from Brighton, UK. We have Naya joining from Oxford, UK. So we'll get to many more in the chat. But the other thing I will call out is the Q&A feature. And if you do have a question, it'd be great if you could put it into the Q&A. It just makes it a lot easier for us at the end to cover off the questions and just keep a bit organized, because sometimes the chat gets very busy. So looks good. The screen share looks fantastic. So we're coming to you first, Aditi. Are you happy? Are you ready to get going?
Yeah.
Amazing.
Cool.
We'll have a great session.
Yes, thank you. Thank you for the introduction and setting up the context. Good afternoon, good evening, good morning, depending on what time it is where you are. I'm working with dunnhumby since 2010, leading the pricing, promotion, and assortment capability based in Gurgaon. Today, with Surbhi, I will be taking you all through the journey of understanding optimization better. Let me take the session forward and start with who we are and what we do. While David has already talked about dunnhumby a lot, but just to give a flavor of where we are coming from, dunnhumby is a global leader in data science, providing retailer solutions, keeping customers at heart of every decision. We deal with transactions of nearly 800 million shoppers around the world and use our knowledge of machine learning to solve problems for more than 50 retailers and thousands of CPGs. We detangle the complexity of retail and big data for our clients using our technical and domain expertise. We will be taking you through one such expertise today. Quickly moving on the agenda, the session is packed with theory and application. We start with understanding the overview of optimization and some related concepts. We will explore the essential tools and methods of the optimization. After that, we will dive into an exploration through practical example and close with few more applications and scenarios before we open the floor for question and answer. Let's get started. Before we get into the optimization discussion, I want to draw your attention to something that we all have done in some form or shape, which is making decisions. If you're a student, you have already made some career choices. No matter at what career stage you are in, what life stage you are in, you have made decision of what to eat or what to cook. We all have gone through the process of decision making multiple times. It's every day that we make choices. There's a common thread that all these decisions have. We try to make best of what we have, whether it's how we spend time, money, or energy. Making smarter choices by considering all options and picking best one based on what matters most is optimization. In simple terms, finding the best way to do something so you get the best result with least effort or waste. Let's get into the example of food again. We are cooking pasta. We might put the water to boil while chopping the vegetables. That's optimizing your cooking sequence, making sure everything is ready at same time. Every day you are already optimizing even without realizing it, right? So if now that we understand that this optimization whole process is an outcome of our decision making, let's explore the different paths that we take for it. First is through experiments. This is about refining the approach based on the feedback. Suppose you are trying to find a best workout routine. You might experiment various exercises, rest period, intensities over time to see what combination yields best result for your fitness goal. Based on these results, you optimize. While this approach is hands on, it can be tedious, expensive, as it involves multiple human iterations and is high on human resources. Another way is also a test and learn, but instead of getting into real experiments, it's the modeled scenarios. For example, we want to plan a trip. You might simulate the effect of flying on a weekend versus weekday, staying in a hotel or Airbnb, and eventually find best balance between cost and convenience. Although it speeds up the process, it requires speed setting up the scenarios and makes the decision process slow altogether. On the other hand, the mathematical modeling is a rapid design process, automating much of the work, minimizing human involvement. Let's look at another food example. Looks like I'm hungry. Suppose you're following a specific diet and you want to optimize your meals to hit your target calories. By analyzing the nutrition content of the meal items that you're getting to, you find the optimal combination and meet the goal that you want to achieve. This requires data. This requires human intelligence instead of human intervention. Each of these pathways offers its own advantages and challenges, and choices depends on specific needs or resources. For the remaining session, we'll be focusing on mathematical optimization. Let's dive into that. Mathematical optimization is a process that helps make smart decisions by clearly defining the problem, creating mathematical model, finding solution, and validating the test results. Let's look at these phases in detail. The first is defining the scope of the problem under investigation. This is done by identifying three principal elements of the decision problem: objective of the study, limitations under which the system operates, and the decision alternatives. The second stage is problem modeling. This is where we attempt to translate this real world problem into a precise mathematical relationship. This process involves taking the key components of the problem and expressing them mathematically so that they can be analyzed, solved, and using the techniques that we have in hand. Third stage is where we get into the solving part of it. This is where we find the well defined algorithms available depending on the problem statement that we are looking at, which has a mathematical relationship established in the previous step already. And the last step is to check whether or not the proposed model does what is expected to do. In simple terms, does it even make sense mathematically or in real world? Optimization as a process is both art and science. Art of describing the model, the problem, and then the model of the problem. The science is solving the model using the algorithm and validating the results. Let's understand this better by continuing our example of meal. Something that we all do naturally every day, but there is a mathematical calculation that can be seen behind it. The situation is that you're planning your grocery visit and you need to decide what to buy and how much for the upcoming week. You figured that this needs to be done with the budget of £50 and you want to make sure you buy necessity items like bread and milk. The goal here is to maximize the nutrition value of the meal. This goal in optimization study is called the objective function. Limits that we work with are the constraints, and the decisions made is defined as decision variables. At this stage, we are defining the problem. The next stage is to express these elements in mathematical form where we get into the problem model. Before establishing those relations, we need to understand the characteristics that these variables can take. Decision variable, it can be integer, continuous, or binary. Constraints and objective function will have multiple variables and elements into it, which can have a linear or nonlinear relationship. These characteristics are important as they form the foundation of the solution that we want to select for the problem that we have in hand. In the next slide, let's look at what does that mean. Looking at the techniques, we start with understanding the nature of decision variable and then look at the relation of objective function variables and constraints. If decision variable can take any value within a range, it's continuous in nature, which takes us to the first node of the flowchart. We now check on the objective function and constraints. If the relations of these variables are linear, we end up using linear programming, else we turn to nonlinear. Moving to the other side of the flowchart, if decision variables are not continuous, we will end up using integer or mixed integer programming. While this is an important factor, there is another dimension that we need to assess while we finalize the method that we want to use. That's the convexity of the objective function. Understanding this property reveals the complexity of the problem. To understand how do we define this complexity, let's first understand the concept of local and global solution. In optimization, a local solution is the best solution within the small region of the problem, while global solution is the absolute best solution across the entire problem. Imagine you're hiking in a hilly area and you reach the top of the small hill. From where you're standing, it looks like the highest point around, but there might be much taller mountain nearby. That small hill is the local maximum as the highest point in that immediate area, but not necessarily in the entire region. Now, let's say you figure out the tallest mountain and the entire region and reach to the top of it. That's your global maximum, the highest point in the entire area and not just nearby. This example so far is non-convex situation, which has peaks and valleys. Convex function, on other hand, does not involve ups and downs by nature. It can be imagined as a bowl, where 2 points, when connected in the curve, will fall within the area of the curve. The visuals on the slide can help in the imagination. Such function will give one optimum and we can be confident about it. While for non-convex, it's a challenge to solve. Hence, this defines the complexity of the problem in hand and helps us choose our technique better. Overlapping this with nonlinear and linear understanding that we just got, there is a relationship can be seen. All linear programs are convex. Non-convex programs can involve either linear or nonlinear programming. But solving them is more complex due to the possibility of multiple local minima and maxima. So far, what I have taken you through is the art of optimization. We understood defining the problem and we understood how to get to the modeling stage of the problem. That's the art, getting into the science with Surbhi on how to solve these problems. Over to you, Surbhi.
Hey, Surbhi, just to jump in, I think you're on mute at the moment.
I'm so sorry.
No problem.
All right. Now that we have understood what optimization modeling is, let's explore some of the tools that allow us to bring this to life. For that, let us first understand what we mean by framework and solver and how we combine them to solve our problem. Optimization frameworks are essentially the structured environments or platforms that provide a set of tools and libraries to formulate and define your optimization problem. They help users to define the objectives, constraints, and decision variables while offering a systematic approach to organizing complex optimization tasks. Examples of some of the popular frameworks include your PyOmo, SciPy, Gecko, Excel, and so on. These frameworks provide a high-level interface, making it easier for the end user to develop and manipulate mathematical models. On the other hand, optimization solvers are the underlying algorithms and software engines that actually perform the computations to find the optimal solution to a given problem. Solvers take the model defined in a framework and apply mathematical techniques to search for the best possible outcome. They use various methods that we just discussed, like linear programming, integer programming, nonlinear programming, depending on the nature of the problem. Examples of some of the well-known solvers include your IPOP, CPLEX, GLPK, etc. If I may give you a quick real-world analogy, think of framework as a recipe and the solver as the chef who executes the recipe. So in short, while frameworks provide the tools to build and define optimization problems, solvers execute the algorithms needed to find the solutions. And together they form a comprehensive system for tackling complex optimization tasks. Okay, moving on. Now, when it comes to choosing what framework and solver to use, there's no universal optimization algorithm available. There's no one size fits all approach. Rather, we have a collection of algorithms, each of which is tailored to a specific type of optimization problem. And the responsibility of choosing the algorithm that is appropriate for a specific problem often falls on the end user. That choice is very important because it might determine whether the problem is solved rapidly or slowly, or whether the solution is found at all. Let's look at a quick comparison of various optimization frameworks across several dimensions. First, looking at the linear problems, all the frameworks here are capable of handling linear optimization tasks. For nonlinear problems, frameworks like PyOmo, SIP, SciPy, and Gecko, they support nonlinear problem solving, making them versatile for more complex scenarios. When it comes to ease of use, OR tools and SIP stand out as being very user-friendly, while others like SciPy may require more effort. For ease of configuration and documentation, PyOmo, Pulp, Gecko, and Excel, they provide excellent documentation and configuration options, making it easier for the users to get started. However, OR tools or SIP, they scored lower here. Lastly, in terms of scalability, tools like SIP, PyOmo, Gecko, they handle large-scale problems very well, while Excel, for example, is more suited for small-scale problems. Overall, the choice of framework depends on the complexity of the problem you're solving and your preferences for ease of use and scalability. Now, once you have figured out what optimization framework will you use to solve your problem, the next step is choosing the right solver that meets your needs. As you can see on the screen, each solver has its own strength and weakness. Some solvers are good at handling both linear and nonlinear problems, but they vary in speed and scalability. On the other hand, some are great for linear problems, but they may struggle with larger, more complex problems due to their lower speed. Commercial solvers, they offer exceptional speed and scalability, though that comes with licensing cost. We also have a lot of open source solvers, which work well for non-commercial projects. So in short, selecting the right solver also depends on your specific problem and constraints. For large-scale commercial applications, Gurubi or CPLEX might be your best bet, while open source solvers like IPOP or GLPK, they are great for academic or small-scale projects. Now let's revisit the example we talked about briefly in our earlier slides. Imagine you're at a grocery store, you have a 50-pound budget, and your goal is to get the most nutritional value from the food items you purchase. You could use an optimization model here to solve this problem and make smart choices when it comes to buying grocery for the week. Let's say you have the data for the food items you could buy from, where you have the unit price along with the number of calories, protein, fiber, and vitamin content that you could use to calculate the nutritional value for every food item. Let's see how can we turn this grocery dilemma into a math problem. In this case, the decision variables are the quantities of food item you want to buy. We set a lower bound of 0, which ensures we can't buy negative amounts. We specify the decision variables as integers since we can only buy the whole units of food. Our objective here is to maximize the total nutrition value, which we calculate as the weighted sum of calories, protein, fiber, and vitamins for each food. The main constraint is that the total cost of our selected food items must stay within the 50-pound budget. Once everything is set, we call the solver to find the optimal solution, which finds the best combination of food items that maximizes your nutrition without exceeding the budget. Now, since we are working with the integer decision variables here and a linear optimization function, we chose the pulp package, which is ideal for linear and integer problems. By default, pulp uses the CBC solver, which is an open source option. However, it also allows us to interface with more advanced solvers like Gurubi or Cplex if needed. Now let's walk through a real-world example with the help of a case study. This is from a project we did a few months back for one of the leading retailers. I won't be diving into exact equations here due to IP considerations, but let me try my best to explain the problem and how we approached it. In our scenario, the retailer wanted to optimize their total store performance by strategically allocating space at planogram level while staying within certain space constraints. So we started by defining the objective function, which is to maximize the overall performance of the store. We had some real world constraints that we had to account for. First one, each planogram had its own minimum and maximum space requirements. Obviously, we can't just allocate all the space to the highest performing planogram. There needs to be a balanced approach. Additionally, the sum of space allocated across all the planograms had to closely match with the total available space in the store. Another key requirement for us was that the space recommendations needed to be in multiples of 2.5 or 4 feet, as those were the standard sizes of planograms the retailer could accommodate. So our decision variable here is the space allocation at the planogram level. Now, once we define the objective function, constraint, and decision variables, the next step was choosing the right Python package and solver. Before we dive into that, could you all take 30 seconds and think, what kind of optimization problem are we trying to solve here? Your options are on the screen in front of you. All right, we can stop the poll, Maddie. As most of you have guessed, the right answer is mixed integer nonlinear programming. And because of that, we decided to go with one of the leading solvers in that particular category. Let me now talk about why our problem fell into this category, why we used mixed integer nonlinear programming. Firstly, we recognize that the relationship between my space allocation and performance is nonlinear. As you increase the space, your performance will improve, but this improvement occurs at a diminishing rate. Nonlinear programming is particularly suited for modeling these complex relationships. We also face the requirement of using integer values for certain space allocations, specifically when we need to recommend space in multiples of 4 feet. Again, mixed integer nonlinear programming accommodates those integer constraints while managing the nonlinear objective functions. Additionally, our problem was governed by various constraints, including the minimum and maximum space requirements and the overall utilization of available space. Mixed integer nonlinear programming provides the flexibility to model these constraints effectively and find optimal solutions to these problems. The objective in our case was to maximize a nonlinear function related to space allocations, and nonlinear programming techniques are explicitly designed for such scenarios. Moreover, these algorithms are robust and they are capable of handling large-scale problems with multiple variables and constraints, which reflect the complexities of real-world applications. Lastly, these methods employ iterative techniques to refine the solutions, which allow us to approach the optimal point effectively. This iterative approach is particularly beneficial for optimizing the objective function, which is influenced by nonlinear factors. Now let's understand how the model works. First, the optimization algorithm initializes the model and it defines the decision variables. These variables represent the space allocations across different planograms in our case. Now, the constraints are applied. This ensures that each planogram space allocation stays within its set boundaries and the total available store space is being fully utilized, avoiding any excess or shortage. Once the constraints are applied, the solver gets to work. It iteratively adjusts the space allocations, aiming to maximize the performance of the objective function. Your performance could be simply your sales, or it could be a combination of your sales, customer penetration, or a few other metrics depending upon your business goals. Finally, when your solver converges on a solution, it delivers the optimal space allocations for each planogram, ensuring that your store layout is efficient and effective. Now let us look at our model results. Once the algorithm is executed, the model outputs the optimal space allocations that maximize your store performance within your defined constraints. It also allows us to calculate the optimal performance that can be expected. However, in some cases, our model wasn't able to find a feasible solution. That happened because there was not enough variation in the space data across historical weeks. But that's okay, as long as we are aware of these limitations and we factor them in our decision making. Sometimes, even failures add value and they can provide insights into the limitations of data or assumptions. Now let's look at some of the broader applications where you can use optimization modeling. Here's another example from the personalization world. Let's start by understanding the problem. We want to allocate the best set of offers to a customer, aiming to make those offers as relevant as possible in order to maximize customer satisfaction. With that in mind, let's break this problem statement into objective function, constraints, and decision variables. The objective is to select the offers that resonate most with the customer, making them feel valued and appreciated. So essentially, we are maximizing the relevancy of offers and in turn, overall customer satisfaction. Now, in terms of constraints, there might be limits on the total value of discounts you can provide or the number of offers that can be given to a customer at one time. Or other limitations could be a validity period of the offer or the availability of the product in the store. Finally, your decision variable here is the allocation of offers at the customer level. Now that we have all the elements laid out, we can use one of the optimization techniques to solve this problem. This not only enhances personalization, but also helps retailers make data-driven decisions that improve the customer engagement and loyalty. For our next example, let's do a quick exercise. Imagine you have a retail client who wants to offer the best prices to its customers. How would you define your objective function, constraints, and decision variables for this scenario? Maddie, would you please pull up the poll? Thank you. So let me just reiterate. Your retailer wants to provide best prices to its customers. How would you define your objective function, constraints, and decision variables for this scenario? All right, we can end the poll. Okay, most of you have guessed it right. The correct answer is option A. So as a retailer, you're focused on providing the best prices. So your objective would be to maximize the profit. When it comes to constraints, your prices must be non-negative. And there might be other constraints as well. For example, competitor pricing, or how you want to position yourself in the market, whether you are a value retailer or a more premium retailer, that also affects the pricing. And sometimes even government regulations also need to be considered. Your decision variables in this case would be the prices of the products. To solve this problem, you could apply the optimization techniques that help your retail client find the best possible prices for their customers. Well, that wraps up our session for today. Thank you so much for your time. We hope this was useful and it gave you good understanding about optimization theory and some practical examples. And hopefully your time was also optimized today. Let us know if you have any questions.
I think our time has been optimized. Definitely. Thank you both. Thank you both very much. If you've enjoyed that, please do jump into the chat, give us a little thumbs up, give us a thank you. Let us know that you've enjoyed it wherever you are in the world. Matthew's put a question into the Q&A, which is fantastic. Thank you very much, Matthew. If anyone else has questions, please, feel free. I've got a few myself, which we'll perhaps kick off with. But before I do, actually, maybe we'll leave that screen there for a minute. So the contact details are there. So if anybody is looking to contact Aditi or Surbhi, grab those details now and follow up with them. We'll give that just a minute and then we'll get rid of the screen share so that people can see us a little bit bigger. But before I do anything, both, here we go. Here's some comments. So first of all, Barry, thank you. Aga, thank you. Great presentation, brilliant session, really refreshing and amazingly presented. Thank you. That was very clearly explained. Good overview. Examples helped. Thanks. Thank you for sharing. Good job. Thank you. Great information. Brilliant presentation there from Tara. Oscar, who was on at the beginning, letting us know he was in Brighton. So Oscar has said thank you for that. Very useful. So yeah, thank you everybody for letting us know that you've enjoyed the session. Surbhi, what I might do, if okay, I'll maybe get you to stop sharing your screen.
Yeah.
And then we'll go into the questions. I think there was a couple of, I've got a couple of specific questions, but I've also got a couple more general questions as well. I'll maybe start a little bit broader, actually. I'll come to you, Aditi, first, if that's all right. But both of you obviously just jump in if relevant. I think the one thing that both of you touched on actually is about defining the problem. And first and foremost, you have to define the problem that you're working on, and then you're working out what model is most relevant and how you want to approach the optimization, all that type of stuff. In terms of defining the problem, I guess sometimes it sounds simple, just define the problem, but I'm guessing actually it could be more complicated than that. So I just wondered if you had any tips or tricks or approaches that you might recommend for people out there when they're first looking at a problem? How do you go about understanding it, defining what it is that you're trying to do?
Yeah, I'll give it a shot, Surbhi, if you want to chime in.
Yeah.
I think it's important to keep the three elements discussed in the mind, right? While it seems very simple to know this is my objective, that's what I want to maximize, minimize, it really sounds straightforward, but it's not. There are scenarios where you really want to identify what exactly is the objective. Do I really want to, is it a minimization problem? Is it a maximization problem? That's really the first stage. And then I think the bigger challenge, once we really get to it, is making sure we cover all the constraints. We can't be covering everything in every scenario, but as comprehensive as we can go, that would be the key when it comes to that second element. I feel the decision variables is the easiest because that's what we are going to get to it. That's what we want to as an answer. But the other two elements of objective and constraints is something that we need to sit down and break it for our problem. Sounds straightforward, but really needs that human intelligence into it.
Amazing. Yeah, makes lots of
Yeah.
sense. What about yourself, Surbhi? Is there anything that you would add to that?
So, like we mentioned, that it's an art, right? Defining an optimization problem into a mathematical problem, it's definitely an art. You definitely need to have the clarity of the business context. You need to have the right people weighing in, which can provide you the domain knowledge. And sometimes, we can oversimplify the problem. We can choose the wrong solver, but that's okay. It's an iterative process. Sometimes your constraints might be too tight. They can be, unrealistic, which might lead you not finding the feasible solution. So you always have to weigh in and see, okay, can I provide some initial guesses to my problem? How close can I be to the feasible region? And once you do that iterative process, you will see that, it's coming together. It start making sense all of a sudden.
Amazing, perfect. Yeah, love to hear that, and explain it as that iterative process. I think makes lots of sense as well. I've got to call it out. Anushri in the chat has just said, "I love that answer, Aditi." So it's great to have Anushri with us, another Data Science Festival supporter. So thank you very much for joining us. The one thing I will call out for everyone, actually, we have now got 5 questions in the Q&A. It is possible also to upvote other people's questions. So even if you don't have a question of your own, but someone else has asked one that you like, feel free to obviously give it an upvote, and then that lets us understand which questions are most popular, and we'll come to those. And what I might do for both of you, actually, if you look at the Q&A, and if you order it by upvote, so I'll maybe take that question at the top there that's from Matthew. Matthew was first in, so thanks for the question. For the planogram case study, how did you maximize the performance of total store without first observing the performance of the configuration, i.e. experimentation? Is one of you able to pick that one up?
Yeah, so I can take that up. So that project that I presented was a labor of 2 years, right? It's not something that we did, in a couple of weeks or even months. We definitely met a lot of our business stakeholders. We tried to understand how best we define the performance variable itself. We tried to play around with different variables and see what makes sense for our optimization problem. And before even developing a tool, we started with a prototype where we model something quick and dirty. Excel is your best friend. We just use an Excel solver to model a scenario and see what our numbers look like. Once we are comfortable with the answers, once our business stakeholders were happy with the results we had in the prototype, we went into full production mode and made this tool scalable to be accessed across the business.
Amazing. Thank you so much. It's great to hear you talking that labor of love as well, working on these problems, fine-tuning it for such a period. Yeah. And a little spoiler, actually, towards the end with the Q&A, it would be good to talk about future trends, actually, and I think where some of this stuff might be going in the future. But before we do that, I'll jump to the next question there, which has come in from Seema. Seema's question was, can we use non-linear programming for linear problems?
I can take that one. Yeah. I think there's nothing wrong in doing that mathematically. The catch is the implications need to be taken care of. Linear programming is the simplest way to look at when we understood the complexity. We know there is going to be one optimum. Non-linear programming will also help, but then it will add the complication because it's meant to do the computational for a more complex problems that we are looking at. So that overhead that we would get using that is something that we'll have to be careful. Do we really want to invest on that, or we would want to go into the oversimplification part of it, as Surbhi said, because sometimes while we are getting into all these sciencey part of it, our mind gets to the complication part easily than the simplification part. So it's all about implication. If we have that power and sources, else linear programming can work with linear answers better.
Amazing. Thank you, Aditi. Surbhi, anything for you to add?
Not really, just that, these algorithms are tailored to specific type of optimization problems. So it's always advisable to use the specific algorithm depending on, whether it's an integer programming or nonlinear programming. And that will save you from additional, computational expenses that you might get.
Amazing. Yeah, that makes lots of sense. And I love that as well, Aditi, what you were saying there around, again, it comes down to understanding the problem a little bit, doesn't it? Do you need to take this to 5-6 decimal places, or, does moving it by a couple of percent have a massive impact type stuff? So that makes a lot of sense. Just coming back to your point there, Surbhi, picking the right algorithm or picking the right model. And as you were talking, I was doing a bit of research in the back end as well, actually. I was multitasking. When it comes to knowing which model to use, and you've talked about it being this iterative approach, but for people that are newer to this type of problem, where do you start? Is there a bit of a playbook that you go to and say, okay, for this type of problem, I'm using this model? Do you have to try it and iterate? How would you go about picking that model to use in the first place?
Yeah. So first you would need to understand the nature of your objective function, right? Whether it's a linear or non-linear function. I think the flow chart that we presented in the slide was very helpful, where you first look at the objective function, then you look at your constraints. Are they continuous? Are the constraints integer values? And depending on that, you bifurcate your problem into a specific category. Now, there are a lot of algorithms available which are tailored to that specific type of problem that you have nailed down. In our example, for example, the final solver that we ended at was not our first choice. We started with something basic, which was Excel solver. And then as we were trying to scale our solution, we had additional real world constraints that we didn't account for in the first place, right? So we found out, okay, Excel is not a good tool when it comes to scalability. We need to have more powerful version, right? So you go about finding and trying different algorithms and see what works best. And of course, you can always, look at your historical data and compare your model output to see if it's making sense or not. Your business users are your, best bet here. They can provide you insights into whether the numbers are making sense or not. So yeah, it really depends on, there's no one size fits all approach, I would say. You just have to understand your problem, objective function, constraints, and see in which area your problem is landing.
Amazing. Thank you very much. I've just
One thing to
refreshed.
add, David, here,
Please.
sorry. I think that's where the validation part of the process comes handy, right? Because that's where we are trying to make sense of the results. While that's the step that's really left to the last, but those iterations that we were talking about really come with those validations, which need the domain understanding, which need the possible techniques available. So it's really the full process that really makes the best outcome that we are wanting to reach to.
Amazing. Thank you, Aditi. I've just refreshed the Q&A again to get the most upvotes. I didn't realize I had to do that manually, so I've just done it. Ignacio, fantastic question there at the top from him with 6 upvotes. So I'll jump into that one. Ignacio's asking, how do you include time, e.g. increase customer lifetime value with multiple objectives, being stuff like profit, environment, and reputation and stuff like that. So could one of you help Ignacio out with that one?
So if
yeah, go ahead, Surbhi. Go ahead.
If I understood correctly, this question is about having multiple objective functions, right? So you do define your objective function, which is typically one variable. Like, for example, in our case, we had performance as one of the variables, right? Now, it really depends on your business needs, whether how do you represent performance, whether it's simply sales or it's a combination of multiple variables like customer penetration or your margin. But ideally, you would want to have a composite variable, which could simply be, weighted sum of all the individual variables, and you need to define one variable which you're aiming for maximizing or minimizing. Now, sometimes you can have conflicting objectives, right? One objective you want to maximize, the other one you want to minimize. There are techniques available out there. I've heard about Pareto optimization, which helps you, balance that trade-off when it comes to conflicting objectives as well.
Amazing, thank you. Aditi, anything for you to add
No,
to
no.
that one?
I was
Happy.
just about to talk about conflicting objectives covered.
Amazing. Thank you both. Thank you very much. Next question there at the top from Aditya. Aditya says, great presentation. Thank you. So that's always nice to hear. Please, can you talk more about the output of the solvers and interpreting the results?
Yeah, Aditi, you want me to take that?
Yeah, please.
Okay. So for solvers, right now, the algorithms that we have in package, everything is so easy. I would say it's like black box, right? With just few commands, you can see the output. So in our case, we were trying to predict the optimal space recommendations. We were able to see that output coming from the solver when we were trying to, execute it. And in terms of validating that, we obviously had our historical data where we were trying to match our output and see if it's making sense or not. So there is no, I would say, not a specific metric or anything which is very difficult to interpret. It's fairly straightforward, especially in the Python packages that you have these days. I haven't at least come across at any, difficult metric that is not very straightforward to understand.
Perfect. Thank you. And yourself, Aditi, anything to add there?
No, I think it's the interpretation that's being taken care of while you're defining your problem statement already. You know what you're reaching as the decision variable. So yeah. I think it's really that knowledge of your problem and how the solver is working at the end gets combined. So still waiting to see that as a challenge.
Amazing. A question at the top there from Mohammed. I will come to both of you for this because Mohammed is linking across data and psychology, and it caught my attention, this one. So Mohammed's question is, what's something interesting that you've learned about customer psychology through running these algorithms? So have you had any surprising results? What's one thing that's perhaps stuck in your mind? And I'll come to you first, Aditi, if that's okay.
Of course, there are surprises, I won't say, but then that's where we go back to our problem. Is that a surprise coming from a really customer behavior, or is it something that's how the constraints have been defined, or the kind of variables that we are looking to define and maximize or minimize? So it's going back to making sure that those surprises are real surprises would be my first step. And then the other ways are external factors, right? As I said, no matter how comprehensive we go to the problem statement, there could be elements that we have not captured, right? Who was ready for COVID? Nobody. There are external factors where we really need to factor in while we are interpreting and reading those results. So surprises, yes, just making sure they're not shocks.
Aditi, what a true data person. I don't like surprises. Also known as an outlier. We're going to find out what caused the problem and
exactly.
and get there. Amazing. What about yourself, Surbhi? You've obviously spent a lot of time analysing customer behaviour and stuff like that. Is there anything that sticks in your mind? Perhaps not surprises, but something that you find particularly interesting?
A thing to note here is that for us, our end users were our business clients, right? Our retail clients who want to use this particular tool that we have developed. So yes, there were surprises where, some of the space recommendations were not making sense to them. But in process of that, we uncovered some of the limitations of the data, right? There were some assumptions that went into our model because of which those results were coming in a specific way, right? So your business users understand, as long as they understand those limitations, those assumptions, they are fine with the answers because these are just the assumptions or limitations, right? You can't really do anything about it. So as long as you factor that in your decision making, I think you can tackle those surprises.
Amazing. Thank you both. Love to hear that. Question there at the top from Pascalis. Have you dealt with cases where the objective function was a trained machine learning model, e.g. a deep neural network? If yes, which tool set, framework or algorithm would you recommend for such scenarios, particularly with scalability in mind?
So
David, I didn't catch the first one. Sorry, can you repeat?
Yeah, so Pascalis was asking, have you dealt with cases where the objective function was a trained machine learning model? If yes, which tool set, framework or algorithm would you recommend for such scenarios, particularly with scalability in mind?
Okay.
So I personally haven't, dealt with deep neural networks, but I do know that, you can use those machine learning or neural network techniques to generate better parameter estimates for your optimization models. They can help you identify the patterns which can feed into your decision-making process. You can even use some of these to approximate your objective function or constraints where they are, sometimes computationally intensive. So you can use some of the probability models out there. But yeah, personally, I haven't really worked on these models myself using deep neural networks.
Perfect. Aditi, anything for you to add there?
You heard it from the expert.
Yeah. We love that. We love that. We've got a couple of questions that we can fire through actually, and then we'll maybe draw to. I'm conscious of time, so I think we've got a few rapid fire questions, and then we'll just perhaps talk a little bit about the future and draw things to a close from there. The question there from Paula. Paula's been having a flashback. So Paula said it's been a while since I've worked on mathematical optimization, so this might be very dated. I used YALMIP in MATLAB to interact with the solvers. Is there anything similar in R or Python? So have any of you come across that before?
I haven't heard of, that YALMIP in MATLAB. Again, like he mentioned, it's very dated. Yeah. But yeah, I mean, we can always explore if there is something similar in R or Python. I'm sure there would be a lot of similar packages out there, but yeah, I'm just not aware about this one.
Yeah, we can have a look at that one and come back. And even if anyone knows in the chat, feel free to help Paula out and drop that one into the chat. Teamwork. There's two final questions in the Q&A there. So the question from Naya, the constraints play a vital role in defining the mathematical problem. How did you define the constraints for your planogram case study?
All right, so this is a tricky question. Again, I don't want to give, exact details since it's dunnhumby IP, but I will try my best to explain. So you can't just allocate all of the space to your highest performing planogram, right? You need to balance your space between all the planograms so that every planogram gets good representation. So you need to have certain minimum and maximum space values across all of the planograms, and you will add them as constraints in your problem definition. Like I mentioned, in our case, the retailer had fixed length of planograms, 2.5 feet and 4 feet. So when they were looking for recommendations of what should be my optimal space, they want those recommendations in multiples of 2.5 feet or 4 feet, and ability to select that valid size essentially. So that also went as one of the constraints in our model. And the other constraint could be you would want to utilize the total available space in the store. You should not be going above what you have available. You should not be leaving the space like waste, right? So you need to have all of these constraints built into your model. You need to define them mathematically, and then that goes as an input into your algorithm. Hope that helped.
Amazing. Yeah, thank you so much. Thank you so much. I'll keep firing along, actually. There's one more question I'm going to come to from Sunny, and then, as I say, we'll draw things to a close. Sunny's question is, dynamic pricing may be effective in improving profits, but can be perceived as unethical. Sunny's obviously tried to buy Oasis tickets in the UK recently. We don't like the dynamic pricing. His question then goes on to say is how to define constraints to guarantee fairness. So is this something that you've come across in terms of, within the models you're working on? Do you have to build that fairness in? And if so, how do you go about it?
So I would just say this, when it comes to optimization, there are broadly two types. One is your stochastic optimization, other is deterministic. Deterministic is when you know all the things ahead of time. So for example, you know how many items are sold each day. You can use that to optimize your inventory, right? But there are sometimes uncertainty. So dynamic pricing could be related to uncertainty, right? It depends on economic factors as well, where there is randomness and unpredictable elements in the problem. Sometimes, modelers used some of the machine learning algorithms or their knowledge about economic conditions, and they factor in as unknown quantities into the model. But for the scope of this presentation and for our work, we have always, worked on the deterministic side of it rather than the stochastic side of it, which deals with more of uncertainty. Yeah.
Amazing.
So I haven't answered that question, what he's looking for.
You've done a good job, though. We're happy with it. We're happy with it. We're happy with it. As mentioned, I'm conscious of time. We've got 2 minutes left. And a personal thing for me, I always like talking about the future. I don't know why, but I find it fascinating. And I think, as having both of you here, you've worked at dunnhumby for 14 years and 10 years, and I'm sure over that time there's been many changes in analytics and retail analytics during that time. And the thing that I'd maybe like to get from each of you is whether you have any predictions in trends over the next 5 years or so within retail analytics. Where do you think things are going? And if you were going to perhaps learn or focus in different areas, what would that perhaps be? So I appreciate I put you both on the spot. So I'll maybe come to you first, Aditi, if that's okay. And then we'll come to you, Surbhi, from there.
I'll definitely start with, it's a trick question, but I can definitely give my personal take on that. It's multifold. In terms of where we think we are going, it's definitely moving at a faster pace as we speak, right? The changes that I have seen in my first 5 years versus the next 5 years are very different. But the common themes around that would be technology, basics of statistics, and really the implementation, the domain knowledge. So while we are talking about the technology speed, that's something that we all hearing now. Suddenly from machine learning, we all are talking about Gen AI. Somebody before that time window will be talking about statistics. So it's about how we are keeping pace of it with the foundations, right? So technology for me will be the steepest that we'll need to keep abreast with. We'll need to make sure we are really keeping up with the trends of that particular tech stack that is being deployed in data science. But now the other elements on it, along with the technology, the other pieces also continue to evolve. So how we really manage those elements, how do we really solve to the problems which are close to the time. We have been doing things retrospectively. In hindsight, we know how to solve problem. It's about how can we be proactive about that domain knowledge. So it's the technology advancement and evolving domain knowledge that I feel together will be really building the trend for any part of data science, not just retail.
Amazing. Thank you very much, Aditi. Fantastic answer. Yourself, Surbhi, do you have any predictions or trends to be aware of, do you think?
I think Aditi touched upon that. AI is definitely, buzzword, I would say. All of our clients are looking for some form of AI in all of our solutions. dunnhumby has already started, looking into those areas. We in fact, already deploy some of the AI models in our existing solutions, and our research and development teams are looking to, how can we make our models more advanced by using some of the advanced learnings. So companies like dunnhumby definitely need to, keep up their game, meet with the expectations of our clients, and solve their problem in real time in order to help them. And all of this needs to be proactive before, retailer even realizes that we need to have a solution ready for them.
Yeah, amazing, amazing. Well, I will draw things to a close there. As mentioned at the start, we've had long-running support from dunnhumby, and they've provided many amazing speakers over the years. And both of you, you had some big shoes to fill. Actually, you were following behind some very good people, and I'm really pleased to say you've absolutely nailed it. It's been fantastic. So from myself, thank you very, very much, and from all the people that have joined at home, wherever they are as well. It's been very, very popular session, so thank you very much. How did you both find it? Did you enjoy delivering the session? Are you happy with how it went?
Definitely. I think the questions were amazing. Thank you, everybody, for posting them. I think it really helps us also keep our brain working on those directions. So thank you.
Amazing. And yourself, Surbhi, did you have fun?
Yeah, I absolutely loved the session. It was my first time presenting, so I was very excited about this, and
Amazing.
I think it really went well.
A natural, perfect. Well, thank you very much. I will draw it to a close just by again calling out dunnhumby. Thank you so much. Anyone watching along, I'm sure you're very aware of who they are now, but check them out, check out their careers page, follow up with the speakers. They're a very supportive bunch. But yeah, thank you very much. And I'm going to end with Anushri there, the best 1 hour spent today, and I absolutely second that as well. So amazing stuff. It's great to see you all. Stay safe, and we'll catch up with you all again very soon. Thanks very much. Bye-bye.
Thank you. Bye.